Hi everyone, my name is Alexander Drajewski. I'm a graphics programmer with more than 10 years of experience. I have helped to design and develop several front-end technologies while working as a technical architect at Ubisoft in the past, and more recently I was working on improving for a engine. And for the next hour or so, we'll be going through some of these improvements, focusing on low-level rendering, resources representation, and management. Before we get started and to set expectations, please be mindful that this talk is more of a technical report rather than introduction of something completely new and unheard of. But I firmly believe there is a fair amount of novelty and common solutions, which I hope you'll find interesting and useful. But first things first, short history of the engine to set context. The Foray engine started around 2006 with an aim to power Metro 2033, a story-driven first-person survival shooter. It was initially designed around deferred shading with completely dynamic lighting, including RSM-based global illumination. In its initial shape, although with significant modifications, it helped to ship multiple projects and deliver them on a wide range of platforms from PC and consoles to VR headsets. With Metro Exodus, the ambition dictated a shift towards more open-world levels and game design. That resulted in streaming scalability and adaptability to become a major design decision factors for core engine systems. Furthermore, while working on enhanced edition of Metro Exodus, it has been agreed to drop support of legacy platforms and non-ray trace capable hardware. Enhanced edition of Metro Exodus was released in 2019 with RT being a requirement. And finally, in 2023, a version of the engine used in Metro Exodus was released for public. It was a long passion project of studio founders and worked out really well with enormous numbers of mods being developed in the SDK. These days, Foray engine supports PC, Xbox Series, and PlayStation 5 only. This is both freeing and challenging at the same time. On one hand, a small set of high-end target platforms with similar features and capabilities make it much easier to develop efficient cross-platform solutions. On the other hand, reliance on high-end features usually leads one into uncharted territory with no established common ways to solve a problem, and we'll be talking more about examples of such cases in a few minutes. Many aspects of the engine designed around ray tracing, including graphics, gameplay, sounds, etc. Enhanced edition of Metro Exodus was one of the first titles to use fully dynamic runtime global illumination solution based on ray tracing, and it's been used and expanded upon since then. Ray tracing is a great tool to achieve one of the original design pillars of the engine, which is to embrace dynamic solutions as much as possible. As to the graphics technology structure, it is somewhat traditional with dedicated main, aka front-end thread, and rendering, aka back-end thread, and extensive workers usage in a sort of SPU style. Reliance on ray tracing and introduction of more advanced rendering systems showed the age of existing low-level graphics code. Originally, it was designed around DirectX 9 API capabilities and evolved from there, and as it usually happens with evolution comes extra cost of abstraction leveling. The biggest shortcoming was on the rendering resources management side, as there was a need not only to move towards retained global scene representation, but also a necessity to support much more complex and dense scenes, which in turn added even higher pressure on scene resources streaming. Furthermore, streaming and resources management parts of the engine couldn't rely on commonly used optimization opportunities because of ray tracing. An obvious example is that one can drop laws of geometry behind camera as it still can be touched by ray tracing. Same goes for lighting, textures, and so on. To keep memory in check, there is a need to stream rasterization and ray tracing parts of the scene and to do it very fast. After the thorough review of challenges ahead, it became evident that improvements in core resources management and streaming will yield the biggest benefit for the time invested. The results of these improvements, as well as some implementation details, will be covered in the next section of the talk. While designing those improved tech, we relied on a set of core design pillars of the engine. High performance was one of the cornerstones of Foray engine, and there was a desire to expand on it even more because of much higher demands on content side. To achieve that, we rely on a close-to-metal abstraction level that still covers all target platforms with least amount of platform-specific code. As such, there is no hard-coded definitions of meshes, materials, even textures in low-level graphics code. Instead, a set of building blocks exposed to middle-level code, which exposes them and composes into what we call common use cases. Also, we embrace the fail early approach to error handling. It means that code should report errors as soon as possible. Where it's possible, we want errors to show up during compilation, thus heavy reliance on static type system. In cases when correctness can't be checked at compile time, validation code should report issues as early as possible at the earliest stage of pipeline. Finally, if errors still creep in, we need an efficient instruments to debug and fix them quickly. So it is necessary to ensure that design solutions are debugging friendly and even design some of those simple debugging tools. And with that, let's move to the first section of the talk. Here I present a high-level overview of so-called bare approach to low-level rendering resources, as well as some implementation details for them. Rendering resources are used on almost every level of the graphics technology. In 4A engine, graphics code structured as 3 aggregations operating on multiple levels. There's the rendering itself, which can be logically split in 2 parts. The middle level part implements resources management, streaming, use cases definition, etc. And software backend is one of the middle level components. It drives command list recording. The high-level part provides a frame loop, rendering passes, and so on. It also contains interfaces which are used by other engine parts to provide data for scene description. And also there's a hardware backend, which handles interactions with low-level resources, execution of recorded commands, memory manipulation, etc. Rendering layers are loosely mapped onto dedicated front-end and back-end threads. These threads are pipelined and utilize work and join model quite a lot to distribute work to other threads. Front-end thread produces tasks for backend to process. It can spawn secondary tasks which don't submit anything to backend directly, although they do access graphics API abstractions if needed. Backend thread primarily pulls on tasks for execution, and upon receiving, processes them with the highest priority, and if no tasks available, helps other systems with their tasks. Rendering resources inherit rendering layers abstraction. At the very core of the graphics technology, we settle with design which is similar in spirit to DirectX 12 and Vulkan. It defines memory, resources, and views as separate concepts and exposes them. They are implemented as a part of the rendering backend. For cross-platform code, they appear as opaque data types. One can only hold them to control lifetime transfer ownership, check for validity, and supply as arguments to high-level graphics code. These 3 concepts used by middle-level graphics code to build common use cases, such as read-only streamable textures, virtual textures, etc. Those use cases are just a simple combination of resources and views, sometimes with manual memory handling and extra logic. Gameplay features, UI elements, and other game-level systems operate with logical textures, which are just an example of such a use case. Resource and view types are similar to those defined in explicit graphics API, with several major differences. It is possible to access metadata buffers and textures such as CMask, DCC buffers, etc., directly from cross-platform code whenever supported. Resources and views follow a strongly typed semantics. They are separate types with no implicit conversions between them. The actual memory addressing preferred over intermediate abstractions and used whenever possible. For example, acceleration structures are just virtual addresses with no resources associated. Also, there is no sub-resources. Views effectively represent them implicitly at construction time, and much more. Having a strong type semantics for resources and views makes it possible to explicitly define supported operations and usage based on C++ type alone. For example, one can set texture resource as render target. It must be a render target view. There is no way to call a function even. Types don't match. One can transition buffer to a depth stencil state. All of those will be compile time errors in most cases. Many errors and usage cases violations detected before code even gets compiled, as offline code parsers IDEs will highlight those issues. Here I'd like to give an example of code operating with these concepts, which hopefully will give some substance to the wordy explanation. The top one is an example of a very simple invalid texture creation, which is used to replace a missing resource. There is just a resource and a single read view there. The bottom one is an example of somewhat advanced manipulation. It creates texture optimized for specific layout and usage patterns, as well as one read view covering an entire resource and a list of write views, aka UAVs, per MIP level. This shows the duality of selected interface, which can be very verbose when needed, or it can be very brief, simple, and direct. Since views are available as a first-class objects, they are utilized to simplify code as well. In this example, we schedule an example of a dispatch call, which writes into multiple MIP levels of a texture. Please don't mind naming here. They are irrelevant and are here to demonstrate only. The first line transitions selected MIP levels into shader write state. one can notice that there is no specification of a target state. The state deduced from view type at compile time so that one can't make mistake of using incorrect one. The next statement schedules a dispatch specifying which MIP levels and where they will be bound. High-level graphics code is free to decide what composition of heaps, resources, and views will represent their use cases or work units. For example, if system provides a functionality to read back data produced on GPU, there is even no need for views at all. It can manipulate with textures, buffers, resources, and other types directly. Or if a system implements a texture streaming, there is no need to manage write views or render target views, etc. It can be just a memory heap and a bunch of texture resources and read views which are moved around from one streaming unit to another. Finally, if system relies on bindless model completely, it can be just a resource and a bindless slot allocated for it. This way, there is no overly complicated Uber texture class that supports all types of usage patterns from read-only textures to depth stencil targets and buffers. To provide global access to texture data in ray tracing passes, Foray Engine relies on bindless resources model. Following the lowest possible abstraction principle, backend implements common interface for it, but it doesn't enforce any management specifics and doesn't impose constraints beside number of the addressable slots. From the user line code perspective, it's just a static array of views. There's a single entry interface, which is to write resource view to a specific location within it. While all views supported, in practice, bindless model utilized for textures, reads, and write views mostly. Because of the way how descriptor indexing implemented on IHV side, bindless is not a great suit for buffers, and one can be better off with buffer suballocation to achieve global indexing. Using a static allocation strategy ensures that resources persist in same bindless slot for the entire duration of its life. This is very powerful as it allows to cache bindless IDs in memory, either CPU or GPU. But then there is a question of dynamic resources and streamable resources. Usually streaming means that actual resource will change upon quality transition. To keep logical resources in same slot and to avoid indices patching in cached locations, instead we implemented double buffering of the bindless array in the backend. Views are flipped between back and front versions. When resource content changes, we just overwrite the view in the back array, while GPU still uses the front array and is not affected. And then when buffers flipped, write operations repeated on the view, which is a back now. On GPU side, bindless model follows CPU representation. Resource is exposed as a simple array with a bunch of casting functions. For DirectX 12, it's implemented with dynamic descriptor is indexing in resource descriptor heap. On consoles, it's just a globally visible buffer named resource descriptor heap that contains unions of buffer and textures. Templated accessors help to ensure code generation won't issue codependent reads on vector pipeline. Wave PSSL compiler tend to do that. They are also used to inject validation code if needed for debugging. There is a fair number of use cases for a bindless model in Foray Engine, and we'll use just two of them to give you a hint of model exposure and level of integration, those being cluster deferred decals as an example of grouped bindless IDs, and analytical light profiles as an example of individual bindless IDs. Clustered plus deferred decals is a primary decaling solution of the engine, designed for high performance with thousands of items per view. It's a bit uncommon approach as it is essentially a forward plus style decals embedded in gbuffer shader and executed at the very end of it. This approach has multiple benefits, such as trivial occlusion culling, fast blending, minimal overdraw, perfect derivatives, access to instance parameters. It's an efficient tool which shines in combination with bindless resources caching. We can use unified access to generic material data to turn any set of textures into a decal with no material duplication, memory waste, or extra code. For lighting profiles, this model unlocks several opportunities. First one being freedom of source specification. It is trivial to use transient resources as light profiles, for example, render targets, per frame generated data, etc. For example, video to the right shows an example of runtime decoded video supplied as a light profile, and same mechanism utilized to generate dynamic light profiles from data-driven shaders and much more. Another one is a consistency. Once Bindless ID is applied, it is consistently available in all lighting passes, from direct lighting to volumetrics and ray traced lighting, which can be seen in the video clip. There is no need to bind these textures in multiple rendering passes, no need to adjust shader code for it, it just works. And finally, there's a memory optimization opportunity, as it's not necessary to keep all profiles in texture array for dynamic indexing. One can't stress enough how flexible Bindless model is, although this should be no news for the audience. It unlocks global access to all resources, which is a must for ray tracing and very useful in many other use cases, as we hopefully just showed. It has been around for a while, and while it still has drawbacks and some differences across AHVs, it's ready to be used as a primary resources addressing mechanism on GPU from our perspective. In fact, with a bit of effort, it can outperform traditional direct binding, not only on CPU, but on GPU as well. We've seen a measurable performance savings on GPU after rearranging code to hide extra latency from interaction. But as with any solution, there's some issues and potential improvements which hopefully can be done once this gets more attention and wider adoption of on the bindless model side. On AMD hardware, one must place resource descriptors in SGPR, while modern NVIDIA hardware these days has no such requirement. This makes it so that optimization for one sometimes means customization for other. To keep code somewhat shared, one must make descriptors uniform across the way. So it's either manual scalarization or decoration with a non-uniform resource index. Both options are scalarization, in fact, which usually implies that helper thread and pixel shader can provide reliable derivatives for texture sampling unless helper lines are masked out. But by doing so on PC, it breaks and invalidates scalarization. Thus, it's up to a programmer to either support multiple sampling implementations or compute derivatives manually or fall back to a single MIP level. Although it must be noted that on PC, AMD hardware helper lines do have well-defined derivatives if there is no dependent memory reads. Finally, some GPU debugging tools still have issues with bindless resources capturing and debugging. Biggest of them is non-deterministic software replay and very slow replays. Now, having a way to put resources in memory and to address them, it's just the first step. Next up, we need to manage these resources and to stream them in and out. This section will go into details of different resource types and their management. For rasterization geometry, index and vertex data stored in one big buffer. Historically, Engine always assumed a small set of vertex format with a very few size classes. Fixed set of format sounds limiting, but it's rarely brought up as a significant constraint for real-life content, though. And when exotic formats actually needed, it usually composed from existing format and some extensions supplied as a second stream. While we still rely on CPU to select resident geometries and their load levels, it's not a preferable option. The goal is to move most parts of scene representation and traversal to GPU in not so distant future. Rasterization geometry can have multiple loads streamed in, with the least detail load being resident and present at all times. Each load contains two sets of indices, main and proxy. Main representation is the set of primary views rasterization opportunities, while proxy representation employed by shadows rasterization and or plus building. Proxy is a simplified version of the main representation that references same vertices. Also, as I just mentioned, some vertex format can have custom extensions to accompany these vertices. With their specific strides. A global geometry buffer is there for direct rasterization and vertex attributes pooling when ray tracing is running. For ray trace geometry, we rebuild class from scratch every frame, as it's highly volatile data, and with instances being selected on CPU, it changes every frame. Ray trace representation of geometries, aka blasses, unlike rasterization counterparts, can vary greatly in size, and their memory consumption doesn't depend linearly on vertices count. That makes fragmentation one of the biggest concerns when managing memory for them. To address them and to achieve faster tracing, most blasses are pre-built offline and streamed in and out alongside rasterization geometry. Also, streaming prioritization is a bit different as it takes into account ray tracing distances, etc. The engine splits ray tracing geometries in 4 different types: static offline, static runtime, animated runtime, and procedural runtime. These types represent different ways to handle and supported features. They're maintained in order of their complexity and performance and memory costs. It's always preferred to use simpler type whenever possible with automatic conversion to simpler types. For instance, skin geometry with a single bone can be converted to static model in almost every case. Doing so enables offline BVH builders for this, which comes with mentioned benefits of extra performance and memory. Unfortunately, offline DVH building not available on PC, and thus static offline type is not used there. Memory management for ray traced geometry is very different when compared to rasterization because of significant fragmentations and much higher memory consumption. All blasses allocated from pools, where each pool is a 128 megabyte buffer. Blasses suballocated from pools using a simplified and streamlined version of a 2-level segregated storage allocator. Pools are created on demand and have a loose defragmentation running on them. There is an upper limit to pools to prevent unrestricted growth. When limit is reached, allocation can fail and calling code handles denial of allocation. In case of failed allocation, it's possible to fall back to least detailed BLAS, which is always present, similar to least detailed LOD in rasterization geometry. While DXR-based ray tracing scene representation gets the job done, it also imposes quite a few limitations which make ray tracing geometry handling more complex and rigid than it could have been. On one of these, and probably the biggest one, is 2 separate representations for rasterization and ray tracing. It goes with high cost and memory and complexity. NVIDIA actually has a promising solution that allows to have unified representation. It's called micromeshes. It'd be great to have a wider availability of this solution or have some alternatives. Another big obstacle is the lack of functionality to update classes and blasses on a sub-level, which would greatly simplify the animated geometry handling and dynamic level of details. Personally, I'd like to see something like a 3-level acceleration structure, which should be easier to do since it's just a software stack change. Having a possibility to feed BLAS builds with in-place produced data can make vertex processing handling so much easier with no need to stream out processed vertices to memory. There's a research within the XR team at Microsoft to implement something similar, which is not part of the specifications yet. It would be really great to have it or something similar in not so distant future. Finally, it would be extremely beneficial to have ways of offline glasses building on PC, as it offers significant performance savings and memory savings. We've seen up to 30 and 40% reduction in memory consumptions and about 5 to 15% boost of tracing speed on platforms that actually support it. For texture streaming, we exploit the fact of almost all textures being stored as a power of 2BC7 compressed data. While it's not strictly necessary for the solution discussed, it makes it a bit easier. Using these assumptions, we pre-allocate a set of resources with different number of MIP levels and then swap them around when texture changes quality level. This way, logical concept of a texture and actual resources with texture data are kind of separated and linked one another when certain quality levels streamed in. Low-level rendering resources and views statically allocated in texture cache and then borrowed by logical textures. Texture cache consists of 7 cache layers. Initial layer is static and contains all the textures available in content. It's never streamed in or out and acts as a sort of fallback. Layers 256 through 1K represent base and middle layer types, and resources here implemented as placed textures. Layers 2K through 8K represent high layer type, and here resources implemented as virtual textures. Each layer of the cache is an array of slots, where each slot is just a texture resource with 2 read views. While each slot has linear and sRGB read view, one of them used in shaders based on implicit knowledge of expected content of a texture. Number of slots in a layer compute based on the layer memory budget and allocated size needed for a single resource. When logical texture gets linked to a slot, it borrows texture and read views so that any access to it will go directly to layer slot that is active right now. As a part of a linking process, read views are written into bindless array as well. This ensures synchronized access to texture views regardless of the binding model used. Here is how cache layers construction looks like for middle layer type. It starts with computation of a single slot size based on supported MIP levels. This information then utilized to arrange resources placement within a heap with respect to their size and alignment. And next, there is actual memory heap being created to host these placed resources. At this point, it's just a matter of populating texture slots with placed resources and respective views. Layer slots don't allocate bindless spaces, though, as they can migrate from one logical texture to another while we want to maintain persistent indices on the logical level. Thus, bindless allocation deferred to logical texture. In case of direct binding model, which is still used by many systems, texture read view passed to a low-level draw called dispatch recording. From there, it's transformed directly to platform-specific view representation, which is no operation, just a cast, and scheduled for reading. In case of bindless model, all IDs are allocated from a single array, and the bindless ID is just a simple 16-bit index sufficient to fetch and to address access statistics for each logical texture. These statistics contain accessed MIP level, number of samples made, etc., and populated by hardware virtual memory unit. Statistics drive GPU-assisted part of streaming prioritization. Streamer relies on CPU and GPU priorities to decide quality levels for each active texture. This process can be described as a downgrade and upgrade algorithm executed on pairs of layers adjacent to each other. The first step is that we select several slots from its highest priority in the smaller layer and the same number of slots with the lowest priority in a higher layer. Next, if priority delta is high enough, we initiate loading of a MIP level matching the higher layer size. While waiting for data, slots are set in pending state and can be elected for transition until it's in this state. And only a certain number of pending slots per layer allowed to control I/O throughput. Next step is that when the new MIP data is ready, we exchange existing MIP levels between layers and upload new MIP level to higher layer. In case of higher layers, instead of copying data around, we map entire MIP level to virtual address space of the upgraded slot. And then steps 2 and 3 that I just mentioned repeated for all selected pairs of slots. The script process has a very good property of self-balances under heavy overcommitment. To get the best of this property, it's crucial to have priority estimation as precise as possible. And to achieve that, we use different prioritization strategies for different cache layers. Cache layers rely on a mixture of CPU and GPU-based estimations. CPU estimation based on the pre-computed textile density and bounding sphere projection for each instance using a texture. While GPU estimation, on the other hand, is the follow-up assisting estimation based on the direct memory access statistics that we mentioned a few slides ago. Both sources of priority have their own advantages and flaws, which fit great for some layers and harm others, so we have to pick carefully. For CPU estimation, it's very conservative and often overshoots, but it's reactive and makes texture requests before they are seen on screen, which effectively shortens latency. For GPU, on the other hand, it is exact. We know a specific level of detail that must be present to satisfy all requested reads on GPU, but it comes with significant latency. To get best of both estimates, we combine them, making CPU in charge of initial, based, and middle layers, and leaving high layers primarily to GPU. For GPU estimation, engine selects 256 textures each frame to report their user statistics. On platforms with access to partial resident textures or virtual memory hardware, this hardware is utilized to write the statistics out. When it's not available, it is substituted by software implementation. In its core, it's just a compute level of detail call with some post-processing. Details are different for AMD and NVIDIA as they tend to tolerate many atomic writes to same memory location differently. We wanted to use GPU estimation to control streaming decision on a submip level, something like a sampler feedback. But while it's a very viable option on consoles, it's still impractically slow to map tiles on PC when they are not consecutive range of tiles or have gaps. It'd be really great to have it addressed finally on OS level by Microsoft, as it will unlock so many possibilities to unify code and achieve more optimal memory consumptions. This figure represents an entire texture streaming pipeline assembled from the components I just described. It has 3 parallel execution timelines synchronized on frame boundary. At the beginning of a frame, sampling statistics from GPU copied to CPU for analysis. CPU and GPU estimate of priorities kicked off for processing in a separate thread. There, they are merged to produce a single priority value, and then those priority values are fed into update process, which we described a few slides ago. Based on decision made in update process, data loading for top MIPS can be initiated. The original CPU thread in parallel processes completed loading requests from previous frames, updates style mappings, write bindless views, and schedules MIP copies operations for GPU. Meanwhile, GPU copies texture data between cache layers and starts scene rendering, which produces new set of access statistics for the next frame. Now moving to the next section of the talk, which covers the custom GPU debugging, inspection, and supporting tools developed while working on resources model and streaming solutions. They were instrumental to achieve correctness and performance goals quickly. Generally speaking, GPU-side debugging experience was and still is challenging at times, but with increasing complexity of GPU data structures and wider adoptions of flexible data models, such as Bindless, the struggling is even higher. It is widely known that GPU debugging is lacking behind that of a CPU, where you can pause execution at any moment of time, inspect entire memory, and so on. On consoles, this parity is lower with unified memory and the ability to halt GPU and attach debugger. But even there, it's still a challenge to catch a state of a certain system then and there. In most cases, it boils down to a GPU capture triggering, which is a relatively time-consuming and disruptive process. Furthermore, to inspect data over time or just see it in real time, we tend to modify shader code to output debug values to textures and then bleed them on screen, which is again disruptive and slow process. While working on Bindless resources model and GPU-assisted texture streaming, the iteration time for debugging and testing was high enough for us to consider building simpler and custom debugging and inspection tools to expedite the process. That resulted in these 2 sets of tools called GPU inspection and GPU extraction. The first one is GPU inspection. It is a very simple communication channel between CPU and GPU that allows network-like message passing. GPU generates messages and can invoke execution of CPU code based on decision made in shaders, which is a powerful tool as it supports any sort of code being triggered. Using shader code to control messages generation allows for very quick iterations, as shaders have support for hot reloading with runtime and recompilation, which makes this feature as a sort of scripting language, if you like. GPU-generated messages are composed with one another to implement next inspection and debugging features. Runtime or live data inspection, logging and capturing, breakpoints and asserts based on conditions defined in shader code, primitive and debug drawing for any information available on GPU, and much more. Since GPU inspection implemented on top of Bindless resources model, like the communication channel is a Bindless buffer resource, it's available in any shader stage and almost any queue type. One, for example, can live inspect data in tessellation shader or ray tracing shader, which is not so easy to debug even with existing tools. This code shows how GPU inspection uses low-level resources and bindless model to establish a communication channel. First, the buffer and view is created to provide a message queue functionality on GPU. The view is written to predefined slot in bindless area so that any shader knows where to find it with no need to bind communication channel or even pass in the index in constant buffer or anything like that. Next, the prefix data written at the beginning of the buffer, it's a message allocation context and has to have some predefined state. Finally, a collection of readback buffers created to download GPU-produced messages to CPU. Some message types can be produced on GPU directly, though. They are just marked as processed and skipped over on CPU. On GPU side, a list of predefined and commonly used commands provided alongside a possibility to build completely new commands and messages. I'll use this example to walk through the message generation process and how they are serialized to communication channel. Here we record command from vertex shader code to draw some primitives and lines. The debug output line function generates a message to draw a simple line from point A to point B with a specific color. It's expanded into a series of allocation and buffer writes to build the line draw message. It starts by atomically allocating message space in communication buffer. If allocation succeeded, the message header was written followed by a payload data. And in this case, payload is just a few floats representing line ends, line color, and line visualization flag, such as control space and which points specified, drawing option, etc. And here's the entire call chain for one message recording. It goes from draw output line invocation to message generation and serialization in communication buffer. The serialization itself is just grabbing a bindless write view and putting a bunch of D words into it. And that's pretty much it. The process side knows how to interpret these payloads based on message types. A following video clip will show an example of live data inspection and debug drawing to visualize ray generation process for global illumination tracing. Here we in a ray tracing compute shader, and we want to inspect ray generation algorithm. Since it's hard to follow this process for every execution thread, we'll filter it to include only those threads that are under mouse pointer or virtual cursor pointer on consoles. That's exactly what happens in is selected by filter function. One can simply move mouse around to inspect individual threads. Once shader is compiled and reloaded, it immediately starts to output inspection data, which you can see at the top left corner. Then we can add a few more commands to output other ray generation parameters and to actually draw a line that represents the ray. Again, shader compilation and reloading, and finally, after a few seconds, newly requested data is available for inspection. And we can see how ray generation changes every frame, the pink line, while being oriented to upper hemisphere on the surface. Hopefully, quick moving ray visualization survives video encoding and streaming. And if not, please check the video once slides are online. Next example shows polygon rendering to visualize data that has geometrical meaning, but not stored as a traditional explicit geometry. Here we use GPU inspection to draw distance map data. The map itself is a result of probe tracing and utilized to prevent light leaking, compute sound reverberation, etc. Those maps tend to have precision problems in complex geometry scenarios, and it's always useful to be able to compare expected coverage and of a probe with actual coverage. In this example, we use inspection feature to draw sphere geometry where each vertex displayed from the probe center by the distance stored in the distance map. It makes it possible to inspect distance map correctness, reaction to dynamic change of probe location and surrounding geometry. Also, GPU inspection provides a possibility to trigger asserts and breaks and even breaks in execution based on condition in shader code. This functionality is very handy when looking for obscure and random issues with no clear wrapper steps. And it's a good tool when trying to catch a source of infamous nuns and infinities, especially the tricky ones when they originate in any sort of accumulation process running over time. The second set of tools called GPU extraction. is designed around a very simple goal to make it possible to capture and retain various resource types for further inspection and/or visualization. In most cases, it's used for making snapshots of GPU resident data followed by visualization, with no need to restart the engine. Furthermore, it makes it possible to capture intermediate processing data from within the shader code itself. Just like with inspection, GPU extraction is available from any shader type. One can use this tool to specify which resource and at which point to capture or extract, control visualization for capture data, build complex view layouts, etc., or even store capture data to files for out-of-engine offline investigation. On this slide, you can see two examples of GPU extraction usage. The top one is a simple texture capturing. We specify GPU profiling tag to set a point in frame for capture to happen, as well as bindless ID of the resource to be captured, and immediately instruct to visualize capture texture in top left side of the screen. The bottom example is slightly more advanced. First, we fill in intermediate image with per thread data that is not stored anywhere else except with GPRs while shader is running. Then we trigger another type of visualization by passing intermediate storage ID to visualize and some properties for actual visualization. Following video clip shows a very simple example of gbuffer laser extraction with custom output layout. Everything initiated and controlled from shader code exclusively. Here we are in Interact Lighting shader, but because the tool itself is available everywhere and there's access to bindless IDs of gbuffer layers, we can schedule extraction from here. In this case, it's a trivial extraction from existing resources. We just specify profiling tags to be the right after gbuffer generation, and once shader is recompiled and reloaded, the extraction starts and runs every frame. This approach to in-place data visualization is rather useful, as one has no need to change CPU code to create extra variable or extra textures or extra storage, then binding that texture to producing shader, adding visualization code, and so on and so on. And that concludes the three topics we wanted to cover today and in this talk in general. Although there's much more left aside due to time constraints. There's more to it in bonus slide though, so please feel free to check them out. And now it's just fitting to summarize the outcomes generated by the solutions proposed. While being hesitant about the per abstraction level with views and resources as separate types, it has proven to be very efficient and surprisingly easy to use and actually very performant. Proposed management and streaming solutions utilize this bare this bare model to address increasing scene complexity and to produce higher visual quality while staying within original memory and performance budgets. Explicit separation of views and resources made it so much easier to lift any traditionally low-level system to cross-platform code. And furthermore, a simplified bindless model implementation by quite a bit. With bindless model, we managed to lay down a foundation for unified shading in rasterization and ray tracing, even more so to improve CPU and GPU performance. Finally, tools developed primarily for new systems debugging happen to be very useful when working on other graphic systems and visual effects. It definitely helped to stick to the fast iteration design principle and even improve on it. But as with any solution, there's a number of compromises and shortcomings to be addressed in nearest future, hopefully. First of all, we are looking into opportunities to unify scene description for rasterization and ray tracing, and also to make ray tracing passes capable of driving streaming decisions just like rasterization does. And second, while view resources split has many useful properties, as we hopefully showed, it's still an abstraction level which has cost, despite being minimal. Introduction of actual resources descriptors and as memory blocks with direct access on and ability to construct, copy, or query them would be extremely helpful to replace views and move towards resources management on a GPU completely. As for the GPU supporting tools, the discussed ones are definitely improvement, and it would be great to at least reach the parity with consoles on PC. On that note, we discussed with NVIDIA at some point the possibility to halt GPU execution for debugging properties using multiple GPUs or just remote machine. And have functionality like that would make an unparalleled improvement to PC GPU debugging experience. Finally, if I had to distill this talk to one slide, it would probably be this one. Hopefully, it represents main messages we wanted to communicate, which are bare low-level resources exposure sounds unsettling at first, but after using it for a fair bit, we are very happy with this decision. Bindless model is most definitely ready for usage in a big AAA project, and it can be faster than traditional direct binding with a little bit of extra effort. Efficient streaming solutions are still pretty much an open problem, especially when it comes to ray tracing representation streaming. A combination of CPU and GPU metrics to prioritize streamer requests is efficient and very performant. And these days, we need flexibility and very fast GPU debugging tools and inspections more than ever as more and more work and decision-making migrates to GPU. And with that, we reached the end of this talk. But before jumping to questions and answers, I'd like to take this opportunity to thank the following people for their help and contribution, either in code or advice or presentation reviews. I would also like to thank AMD, Microsoft, NVIDIA, and Sony for their valuable insights and suggestions that help to design solutions presented in this talk. A lot of talented people helped indirectly by sharing their knowledge and experience, and this talk would have been completely different, if at all possible, without the influence of these sources. So should you want to dive deeper in some of the topics mentioned throughout the talk, please check out this list. Also, I encourage you to look up deck once it's released, as it has quite a lot of information in speaker notes and some bonus slides. Also, if you are interested in the low-level graphics code, ray tracing, and general engine architecture, check out these open positions and look up the links attached. Thank you all very much for tuning in. I really hope it was useful and justified investment of your time, and I'm happy to answer any questions, and I do hope you have some of them. Thank you.
Thank you so much, Alexander, for that excellent presentation. Alexander is now joining us now to answer some questions, of which there are many. We'll try and get through as many as we can. By the way, it's great seeing so many familiar names in the Discord chat. I know it's only a virtual conference, but it's really good to see you all. So let's just kick off. One of our first questions is from Michael Vance. Oleg, can you describe the bindless caching from the decals clustering more? Mike's wondering if you're not just talking about sort ordering based reuse.
Yeah, first of all, just to make sure, can you hear me well?
Yes, we can.
Yeah, so with bindless caching, what I meant is that we try to put in memory decal descriptors and keep them intact as much as possible. And I believe I touched that topic in one of the slides about the synchronization of bindless, because there are different ways how you can access bindless resources, but usually you use some sort of indices. And it's fine if resource is intact, but as soon as you start streaming that resource, it means that the actual resource and view will change. So you either have to patch those indices in GPU memory because decals were cached there, or you have to actually update views in a heap. So by caching, what we did is that we essentially used the second approach. And that way, we don't need to update indices of textures accessed by decals when they got streamed with higher MIPS or like lower MIPS.
Cool, thank you. Let's move on to our next question. This is from Glass Beaver. Just a reminder, please use your real names on Discord. We really appreciate that. Why are buffers slower with bindless?
So yeah, as I mentioned, I believe in one of the last slides, that with bindless, generally you just get extra level of interaction, which means extra latency. So if you have ways to hide that latency, it shouldn't be a problem. And that's what I meant, that you can get performance gains if you essentially structure shaders around that extra latency to hide it. And with buffers, there are a very small number of, there are very few opportunities to actually hide that latency, especially if we talk about buffers for geometry, because vertex shaders, they are not that of a complicated, and there is not that much of a possibility to hide latency. And actually, if you try to measure like the bindless vertex and index buffers on any like current day hardware, you will see that it's generally significantly slower if you do so, because like the easiest way to access memory is just to use a pointer, and buffer is just a pointer. And if we add pointer on a pointer, that's like an extra round.
Cool, thank you. So our next question, we have Jussi Nutella, who says, how do you ensure that resources in the global bindless heap have correct barriers applied?
Yeah, so that's also something that I hope I touched in one of the slides, that we kind of cheated because we don't place all resources in bindless heap. We tend to put only read resources there. So we don't have that extra barriers needed for write resources. Like we do have a very small subset of write views in that heap, like for example, for debugging stuff and whatnot. But with read resources only, it's much easier to guarantee that all resources will be in the read state, because they tend to be, in most cases, just readable resources, like for example, textures on materials and whatnot. So that way we just make sure that before we start the frame, like when we do synchronization of double buffering indices or bindless heaps, we ensure that by that stage, all resources that are supposed to be touched in bindless buffer will be in read state, and that's pretty much it.
Cool, thank you. We now have a few questions about your blasts that I'll group together from Michael Vance and Alpa Ozcan. So wondering, first of all, how much disk space did your blasts end up taking? And also, how do you deal with animated geometry if your blast is computed offline?
Yeah, so to begin with, there's no way to pre-compute all blasts offline, because essentially we can put only static meshes in acceleration structures. So you have to build some blasts like animated or just skinned, or if you have some vertex animation in runtime. So that's essentially what we do. We pre-build and bake in offline only those blasts that are not going to change geometry in runtime. And that also leads to the answer to the first question about the size of. It depends on how much of, like, if you are considering doing something similar, it depends on how much of your geometry can be static. We tried really hard to find all the heuristics, like how to convert animated meshes in static meshes. Like for example, the one that I mentioned in the talk. Like we have a lot of skin geometry which is not actually animated. We use bones like to hide parts of geometry, or just to move a part of, or like entire instance, because that's just easier. And we detect all of those cases, and then we kind of promote those meshes to static meshes, because they are faster and we can actually build them offline. So you generally want to have most of your geometry static. And in our case, it depends on the platform, because different, like on consoles, they have different builders for blasts. And average, I would say that it's something around 1 GB to 1.5 GB, but that's compressed format. So with compressed format, you have to, like when you actually going to use that information, you have to supply index and vertex buffer to decompress it. So yeah.
Cool, thank you. I think that answers their question as well. I really like this question. Sorry, it's another one from Mike Vance, but talking about your architectural stack and your layering for the renderer, I think the way you'd had the sort of the front end and back end, when have you had to break your abstraction in the most egregious way, and how do you later address it?
Yeah, so to be completely honest, that layering stack, it's not something that we, how would I say it? It's not an ideal solution, I would say. There's a lot of legacy that influenced that split, but with this new resource model, the biggest like the biggest sort of break that we had to do to like to address these abstractions is with ray tracing part of the engine, because originally it was integrated as a sort of a completely isolated part of the engine on the side. So it didn't actually touch the resources model. It handled everything internally and had different implementations for different platforms with no higher abstraction level. So to address that, we had to like restructure quite a lot of that code, but it also allowed us to actually fit in this new resource model. But still, like with this acceleration structure and everything, it makes sense on PC to have a separate resource type for acceleration structure, but on consoles, it's just a virtual memory pointer. So that's what we ended up doing. It's just a virtual memory pointer.
Cool, thank you. And then we've got time for just one more question. And this one's got quite a few votes up. So this is from Tom Everett. Has the extraction tool you described been considered for catching in the field bug reports from players?
That's actually a great question. Honestly, we didn't consider it, but now as you mentioned it, it's probably something that we will look into. But originally, yeah, it was mainly to debug something, like use it in developed builds to catch data which is present for a fraction of a second or for a frame or something, because that's really hard to do with like a conventional frame capturing tools and everything. But yeah, as you mentioned, like catching a place where none's generated is probably a great idea for like the actual users.
Cool. Well, thank you so much, Alexander, for answering all those questions. I know there are so many more on Discord for you. I think we've marked the ones that I asked you, but if you have the time, I know everyone would really appreciate it if you could go and engage in that conversation. There's loads there. So sorry to everyone who I didn't manage to get to ask. We are going to go into a break now, and we're going to be back at 9:30.